These are the wrong ones. Yeah, that one switch off. So no, the other way around. And the one above it is for the other lines.
That makes more sense.
Yeah.
So hi everyone, I'm Xuanrui from the Graduate School of Mathematics at Nagoya University in Japan. So today I'm going to give an overview of what we know about, and mostly what we want to do for algebraic curves and synthetic algebraic geometry. So I'm a PhD student at Nagoya University in mathematics, and my interests are in categorical logic and sheaf topos theory. And I am not an algebraic geometer, so I expect to make lots of mistakes on the technicalities of algebraic geometry. I know a little bit, but my knowledge is not that great, and I have to say I never really got to the core of it. But if you spot a mathematical error, please correct me immediately. And this is just an overview. So everything I say could turn out to be true or not, or who knows? But I'm just sharing some ideas. So let me just set everything up. So why do we want to do synthetic curves? Because curves are basically, they're always the first objects you ever study in algebraic geometry. Even if you're working, of course, even if you're working in a, say, classical that is pre-Grothendieck type of approach. So, but even in more than scheme-based algebraic geometry, usually curves are the easiest, the most common type of examples, because they're simple. They admit a very simple classification, which depends on only one thing, the genus of the curve, but they still require a considerable amount of machinery, because the result that classifies curves, is basically Riemann-Roch, and that requires you need to know about divisors, cohomology, and all of that to state and prove the theorem. So it is a relatively simple and class of objects that we know well about, but it is nevertheless very non-trivial. So I think that's why they're so ubiquitous in algebraic geometry as, say, phrase examples. So it's a good that makes it a good test bed for ideas. But if you go say up one dimension, if we work with surfaces, then you will have all kinds of non-trivial difficult problems, like resolution of singularities, and also the entire classification thing becomes much more difficult. So
Well, I have one comment. As you asked for these, I mean, I think it's a bit dangerous to say that classification depends only on the genus. I mean, it's one invariant, but I mean, when you fix the genus, you still have a whole space of curves with that genus. And
yes,
I mean, there you can do sub-classification.
Yes. But usually we classify curves by genus. It is that's the right way to put it. Usually. Classification of curves by genus. I know you can. I know there are many more invariants like degree. So, well, there are actually more. Yes, there. What you said is very true. There are actually more ways to classify curves, I guess.
Depending on what you want. I mean, topologically it's everything, but I mean, algebraically it's a coarse classification. But yeah.
Yes, the most yes, maybe the right way to say it's most textbook treatments of curves classified mainly by genus. Well, also because they're coming kind of from a complex geometric point of view, so I guess that just makes more sense. So let's first define a curve, of course. So usually curve is defined as an algebraic variety, which is a reducible reduced scheme, and which is separated in a finite type over a field of dimension 1. So this is actually a pretty long definition for something that is supposed to be so simple. So how can we define them? So irreducible and reduced, irreducible already has a definition. And reduced, irreducible and reduced should just have very similar to the usual like non-synthetic definitions. For example, I would expect a reduced curve, a reduced scheme to be something that cannot be written as the union of two non-empty schemes, and with that you can also prove things like obvious statements like the spec of a irreducible curve is irreducible, and I have not proven it, but I think I know how to prove it, and hopefully that works. The more tricky part is a finite type, because we don't know if a finite type is actually a useful.
Did you talk about irreducible now or about reduced? I mean, reduced is a bit tricky.
Yes.
We have candidates for that.
I was talking about really.
And you can't define it in the normal way that you say the algebra is reduced. So
yes,
that's something we know like doesn't work. And irreducible, there's some definition.
Irreducible is you can use the same definition. A finite type is also a bit more tricky, so I have to actually edit that line out. But yes, you can define a finite type like in the usual way, but I'm not sure it is useful.
You are reducible. I mean, so let's take a family of quadrics in the plane that at some point degenerate into two lines.
Yes.
Mm-hmm. So at special points, the family is not irreducible. And this is just an example for that irreducibility does not is not stable under phase change. And I mean, in our topos models, things should. I mean, we implicitly base change all the time. Because we consider all, I mean, you start with our ring K and consider all K algebras.
Yes.
So I mean, what's
so it's like could really be only so you could really define.
I don't know how to.
So I guess you could really only define irreducibility over, say, R, but not in general.
I mean, we have a candidate definition which kind of worked. So I don't know.
Like that didn't really irreducibility over R.
So I would guess the candidate definition that we use means being reduced even after change of base.
Being still irreducible.
Still irreducible, yeah, sorry.
What is the definition?
Oh, what was it again? Every non-empty open is dense, I think.
Yes.
And dense means if you have an intersection. Wait. If you intersect with something open and the result is empty, then the open intersected with is empty.
Yeah.
So you can say a subset is dense. Okay. And then you say every non-empty open if it's dense. I mean, which is one of the classical things. And I mean, it turned out a couple of the classical equivalent ways of saying irreducible works.
It works at least it works as at least when you're basically working only over the implicit base ring.
Yeah, I mean, all our schemes are schemes over the base ring. So. And I mean, reduced, we have a candidate somewhere which says that every nilpotent element of the algebra is not zero. And
Yes.
That's something which seems to work kind of, so it might need some refinement, but it's okay. And I mean, for finite type, you can actually drop that one because our schemes are always of finite presentation, which is stronger than finite type, but I think it's actually what you want. So
I don't
finite type
think you need finite type in that case.
already in the definition of.
We discussed it a few days ago, actually, so I don't think we actually need finite type. Yes, and for separated schemes, are they automatically separated? I don't think so, but I think you can always try the usual diagonal map definition. I have no idea whether it will actually work. I think it
actually works.
I think it probably works. So
you can say the diagonal is closed, or you can say just equality types are closed propositions, and that one actually works well as a synthetic definition.
Yes. So
separated.
For dimension, we all know that every scheme is a formal manifold or of space in the sense of synthetic differential geometry, and we can always steal their very well tested, well-known definition of dimension, which is not exactly trivial but usable. So from SDG. The question is that will that actually give us the right notion of dimension? I don't see the reason it would not, but it would nice to have a proof that it actually say corresponds to relative dimension. So yes, another thing that we have to keep in mind is that we're actually Riemann-Roch is a quite classical result, meaning that was developed. I don't remember, but it has been around for like 100 years, way before schemes and the relative point of view was invented. So we have to be careful. It is kind of an absolute result, but we're working in relative settings, so we have to be kind of careful. But also we need to be working over a field, and that is a very difficult part because in synthetic algebraic geometry there is no way to work over a field. So yes, so we all know that R is actually the base ring R is actually a field in the constructive sense. So meaning that if we know that an element is non-zero, then it is always a unit. But of course that is we're very sure that that is not the right analog of working over a scheme over a field in traditional algebraic geometry, and we also know that so we know that it is know that externally R is just the R corresponds to the vector of points of the affine line over the base scheme, but we say we want to work over we want to be working over a field, but and if we're working over a field, then R should correspond to the spectrum of KT, right? But it is not actually I don't think it's actually possible to like force this using an axiom, because you can always take size toposes, and the base scheme will no longer be a field. So it's not possible to force our base scheme to be a field, base to be a field, and using purely categorical logic means. But there are always workarounds. You can use always use a modality. This is what Ingo proposed during the last SAG workshop. And unfortunately, Ingo is not here this time, but that's definitely a way to work with, potentially a way to work with specific bases like fields. Another solution is possibly to work in the FPPF topos, because if I recall correctly, in the FPPF topos, there's this basically there's this property that the base string is algebraically closed. So that but is that the right topos to work in? I'm not sure about that. Another solution is to just ignore it and wait until we get stuck. And when we get stuck, if you get stuck, you can always do some reverse mathematics to see what axioms are missing and whether they're reasonable or not. So that's that's a solution that's basically a non-solution. So let's go to the statement of Riemann-Roch theorem. Classically stated, it says for any Cartier divisor on the curve C, there's a natural number G called the genus of C, such that this equation holds. So well, LD is the dimension of the space of global sections of a line bundle associated to the divisor D, and deg D is the degree of D, and K is C's canonical divisor. So this is a pretty big definition, but I think there's reason to believe that these quantities can all be defined synthetically. So first of all, you need to know what divisors are on curves or on varieties in general. So there are two different but related, and I think largely equivalent notions of divisors, Weyl divisors and Cartier divisors. So for curves, usually Weyl divisors are much more straightforward to work with, because Weyl divisors are just formal linear combinations of codimension one subvarieties. In the case of a curve, the codimension one subvarieties are just points. So it's just a formal linear combination of points. And this actually makes a lot of sense if you think about the complex analytic case, because it just tells you how many poles a function something has. So it seems that there's no way to really get a degree from this linear combination. So I think Felix proposed that it's better to understand it as a function that maps varieties to an integer, and this is kind of to an internal integer.
Proposed a couple of things, but not that one. I mean, the problem, if you like copy the classic definition where you say you have a linear combination of
yes, that doesn't work.
Points. I mean, it can work if you say I take the free abelian group over
yes, you will have to
the whole curve. So that could work. I haven't looked into it. What I looked into and proposed once is that you look at maps into some extension of the integers. Should be called the upper integers, because then you have this operation diff, which takes a rational function and gives you a Weil divisor from it. So I mean, that's what I proposed.
Yes,
but
so
it's not clear how you turn that into a line bundle, but for Cartier divisors, it's clear how to do that. So, I mean,
yes, Cartier divisors, that was what I found. So, so Cartier divisors are actually easier, since probably easier to work with synthetically. Will divisors maybe less so? Maybe you can get something from the free abelian group over the curve, or more generally over the set of codimension one subvarieties. But what can you do from it? What can you get from it is still unknown, especially we are interested in computing the degree of each divisor, which for Weil divisors it is just the sum of all coefficients. So if you have a free abelian group, I'm not sure you can write that function, but I suppose it has to be a function to the upper bounded integers as well.
Okay. Yeah. That might work.
I think you can define a degree function from a free abelian group.
Yes.
Okay, because it's finite sum. So
it's finite sums. So.
Oh, but you have the problem of the minus.
Yeah.
Yeah, okay, no, not so clear.
So yes, the minus. Yeah, I'm not so sure. Maybe in this case it's kind of helpful to think about the complex analytic picture. I'm the saying I'm not too sure about that either, but yeah, you should think of Weil divisors as something that basically computes the degree of poles. So in the synthetic setting, that could be a more fruitful way to look at them, instead of just the free abelian group, which doesn't really give you any information. Well, if you're not working synthetically, if you're working like classically, you know that a degree always exists, but it doesn't give you it doesn't give you like a way to actually compute it. That is, unless you know what your divisor is. So, Cartier divisors are maybe easier to work with. So Cartier divisor is a Cartier divisor is a global section of M cross over O cross. M is the so M is a sheaf of if I remember correctly, it's a sheaf of algebras. If I'm recalling correctly.
But I mean, we can't add things. You can just multiply things.
Yes, the multiplicative group.
Yeah, so it's not an algebra.
So, but if we throw out all of the sheaves and go into the internal perspective, which hopefully all of us kind of have an idea how to do. It's just a type of like local rational functions in X, quotiented by the multiplication of like locally defined function. So if the local functions are not only rational but regular, then the divisor is called effective. So I'm not too sure about that, but usually when you say when you say it's regular, when you say a function is regular, you mean that it's identically defined on all of you. I am not sure how to express this condition. But I suppose it's pretty similar to that, because you have you can say for a rational function you have a covering by subsets, and they're defined, and it's defined on like each of the quasi QC opens. But for a regular function, it looks like it's just like a function.
Yeah,
So
it just works.
But I would actually propose that in this case, it is very helpful to connect to the complex analytic picture, because at this point it occurs to me that it's actually very close to what I'm usually doing in complex analysis. So maybe for what we're doing, holomorphic and meromorphic are more suggestive, more like they're better names. Just thinking, because in algebraic geometry, I've seen some sources use meromorphic and others use rational. So I don't think it's going to cause a lot of cause lots of problems, but I don't see anyone who is not actually working in complex geometry use holomorphic in place of regular. So that might be a little bit confusing, but once someone gets a picture, it should be pretty clear to them that holomorphic and meromorphic are like better descriptors of this picture, and with regards to like similarity to the complex analytic case. So we know that effective Cartier divisors are often defined in terms of ideal sheets of subschemes too. So can we mimic this kind of kind of correspondence synthetically. So I don't know. So yeah, in classically, when we have a subscheme, there's a ideal sheaf associated with it. But here, well, of course, if we have a kind of an inclusion of some inclusion rings, we can obtain some somehow obtain a ideal of some sort. So I'm not sure how we're going to mimic this kind of definition synthetically speaking. So this is a bit technical and it's not something I'm good at, but so we'll have to consult a real algebraic geometer, but I think there should be some kind of similar correspondence, even synthetically speaking. So while the divisors are synthetically can be tricky synthetically, you can define them this way, but you need to z, but I said z, but you actually need upper bounded integers. So in the case of the curve, it's a function from the point to the upper bounded integers. The case of Riemann surfaces gives one a good intuition, because essentially what divisors were used for was basically to compute the number and degree of poles somehow. But we probably cannot go from linear combinations to this function. And can we? I'm not sure. Can we go the it occurs to me that going the other way should be pretty straightforward, because you just computed this at every point and then computed at every point and then injected into the free abelian group. I'm not sure you can compute the degree of some. That goes back to what we were saying. I'm not sure you can compute the degree of something in the free abelian group with all the negatives.
Also map from C to Z, they cannot isolate a point, if you see what I mean.
Yes.
So if you have a curve which is irreducible and has a point, then it's connected, and then every map to the integers will be constant. So,
yes, so it has to be upper bounded integers.
Yeah, I mean, with upper bounded integers, it might be different, but I just proposed those because then you can define what the divisor of a rational function is.
Yes.
But for any other thing you might want to do, I have no idea if that helps you. And
yes.
I mean, for the free abelian group, I don't know if you can define a function which computes the Weyl divisor of the rational.
We'll have to, yes, you can define the free abelian group, the group of divisors, which is just a free abelian group. But the more important part is to have a way to have a method to compute the degree of each divisor. Otherwise, what are you using these divisors for?
Well, I mean, the symbol C stands for two different things. I mean, so one, it can be the scheme C, which is what you were talking, what you just talked about.
Yes.
Or we can just take a look at the k-valued points.
Yes.
Let's say k algebraically closed, classically, and then I mean, but this is just a set.
Yes.
The k-valued points, and then it makes sense to consider a map to Z.
Yes.
And yeah, so I mean, it's, yeah, and I mean, it doesn't. I mean, it classically also doesn't make sense to take a back from the scheme to see.
Yes, classically, it really only makes sense to look at the k value points. So, but if you look, but if you so the question is whether you can get a computable degree function out of this.
Yeah, but then you want I mean, you want finite support. And
Yeah.
so yeah, actually you're not looking at functions, which is an element of applied type, but you're looking at a finite linear combination, and not.
So yes, if you take the first set of k points, there actually might be a chance that yes, you're right about that. If you look at the set of k value points, then there's actually a chance that you might be able to get a computable function that computes a degree. You might be able to get so you might be able to define that function, but of course you have to define it. And also again, that requires some assumptions, like if K is algebraically closed, and we're not sure how to mimic those conditions synthetically. So that kind of springs back to what I've talked about fields just a while ago. So, oops. So Cartier divisors have a correspondence to line bundles, and we already have a good understanding of line bundles synthetically, fortunately. So in the case of curves, we can use that to define the degree of divisors. Yes, and there are also many other approaches, but don't ask me about that because, again, I'm not a real algebraic geometer. So, but once you have L and the degree of the divisor defined, you can proceed to state, not even prove Riemann-Roch. So once you state it, you want to prove it. There are many existing proofs of Riemann-Roch. There's so the most well-known proofs use their duality, and it's available in many algebraic geometry textbooks. So it requires some homological techniques, and I don't know if it's going to work well. I'm not even sure if it is valid constructively. It looks to me that their duality may be valid constructively, but even if it's correct, you will have to find a way to actually prove it without resorting to projective and injective resolutions. So there's also a simple algebraic proof that you can find in, for example, the book Algebraic Curves by Fulton. That might be helpful, but there's also a complex analytic proof, which is unlikely to be, which is of course not completely useful to us because there are no analytic tools in our setting, but maybe there are some idea. But as I pointed out, there are some obvious similarities to the most simple and classical Riemann surface situations. So even if don't have access to those complex analytic tools, it might actually give us some interesting ideas, and there might be some way to just circumvent all the analysis. So, but this is the part we actually know least about. So, I have zero idea on which of these potential approaches will work best, or maybe there's also a good chance that none of them will work. That will have to figure something new out. But sure, I'm very open to hearing new ideas and things like that. So once you prove Riemann-Roch, you can complete the say textbook classification of curves by genus. So naturally, you want to move towards surfaces, which are way more complicated. So interesting ideas might include doing blowing up, some basic birational geometry in pastry surfaces, and also the classic result that there are 27 lines on a cubic surface, which seems to be a pretty concrete result, but requires a lot of computations. So as I've mentioned earlier, as I've said to some people here earlier, so I think a common problem in synthetic approaches is that often it can be much easier to state abstract big results, but often you don't actually know how to compute things, because say you have no, well, it is not like you have a systematic way of computing things classically either, but often you can use some tricks to compute things, say cohomology groups, but some of those tools are simply not available constructively, and in some cases you cannot even say constructively define a function that compute those things. So that's always a strange dilemma. It's while it becomes easier to state big results in abstract things, it can be sometimes like small computations can be much more difficult. As I've said, for example, it's not even possible. It's not even clear if it is possible to define a function that takes a divisor to its degree. So, well, classically, kind of hand wave around it, and you know it always exists. But here, when you define a function, you actually need to actually know a way to compute it. So that could be a blocking factor. And also I would see it interesting to connect those things to complex geometry. So well, naively, we already have a good theory of synthetic differential geometry. So naturally you would ask, if we just replace R by C and replace, say, smooth by holomorphic, what will happen? I don't think it will be a good idea, but at least I think we're going to get somewhere just by doing that kind of naive replacement, and eventually get stuck. So I was wondering if we could basically connect the algebraic case with the complex analytic case and prove some comparison theorems in this context. But if anyone has more ideas than I do, please just talk to me. So I think that's it. I'd like ask lots of questions and propose lots of ideas without answering any of them. But of course, I would love to hear answers and also more questions.
Okay. There's some questions.
So there are any questions? So we also have time for like some discussions.
One comment. And
Yes, please.
when I wrote this short note where we calculate something on elliptic curves, which I mentioned earlier, like the results at least, and there's also a proposal for a definition of curve, and it says it's a projective scheme.
Yes, it's a
closed subset. That's something you didn't consider.
Yes, I didn't talk about it. It has yes. It has to be projective, and we have a definition of projective space. We can define some varieties.
Yeah.
Some the schemes of projective space. We even have a project construction. So, and project construction. We even have a project construction, and I've even tried to prove that that like P1 is the product of Rx. And it's a I didn't actually get stuck, but there's like yeah, you need a little bit of algebraic tricks with that, but it's actually pretty straightforward, and I think that's at least a good sign that our synthetic cross construction is actually right and actually works. So, but yeah. But then later you might want to prove that the project something is always a projective scheme. That would be more difficult. But yeah, but no, yeah, it boils down to finding the right injection.
So one question is also smoothness.
Yes.
Because so for synthetic scheme, we have a notion of smoothness where we can define the dimension.
Yes.
And so I was thinking, at least in a first approach, maybe just consider projective smooth curve.
Yes. There is yes, I think so. Is there so algebraic geometrically speaking, is there actually a good reason to consider singular curves?
You have all the reason to consider singular curves, but I mean, we have different less results than the smooth curves, because I mean, for a lot of things it's important.
Yeah, yes, of course.
I mean, Riemann-Roch is for projective smooth curves.
Yeah.
And I mean, they know how to say dimension one.
Yeah.
So this is quite.
I mean, well, of course, organic part of an abstract curve is, I mean, not embedding, but then you need Riemann-Roch to construct enough functions on this curve so that you can embed it like, into projective space. So I mean, this is, and a posteriori, we know that they are projective. But I mean, I think it's okay to put this. I mean, then it's easier to
begin with the smooth case.
Yes. And against the smooth case. Also, the smooth case is just, I guess, more important, right? I mean, there's a reason to consider product to consider singular curves, but most results are for smooth curves.
Yeah. So also, for me, it's a question that I ask a bit more generally. So just using the divisor, the free abelian group generated by the curve. Why not just do this?
Yeah, I mean, we should definitely consider that. I mean, what I don't know is in which situations, if you can build a diff, like which computes the divisor of a rational function. That's why I proposed, that's the only reason I proposed this upper natural stuff.
Okay, you cannot go from a rational function to the free abelian group.
I mean, maybe you can,
but we don't know.
Don't know.
This. Okay.
You don't know, and yes, yeah, that's a good question because again, you want to, if you're just like considering similar parallels as the complex analytic picture, you can always kind of want to know how many you kind of compute how many poles there are there, and like it's the degrees of those poles. But yeah, I'm not sure that but I'm not sure that's always computable, even if you think about the complex analytic picture. So it's not even a priori computable.
Constructively, it sounds very optimistic to want to compute it.
Constructively, we will reduce everything to the complex analytic picture. See that for many things it doesn't really look like you can compute it at all.
Yeah, I see. One thing I consider as well, but I'm not sure it's helpful. But there's the question of flatness for those curves, and I guess they should be assumed flat.
I guess they should.
Maybe it can help compute the degree.
Do we have any results about flatness?
Not much. No, not much.
And in particular, we have no result which shows that the smooth schemes are flat. So
I wonder why maybe smooth just it's enough.
But here we have the option to throw flat in.
And we don't even know if flatness is the correct conditions synthetically.
And I'm not sure about the comment that it's too far away to do constructive calculations. I mean, in our context, yes, but if we had a discrete field constructively, then I think which can just do the calculations as any computer algebra program does.
But we don't have to.
My outcome is that so in Ingles Nabla modality, we should be able to.
Yes, but we need to have a discrete field, which is not that. I guess when we have a discrete field.
Of course we don't have it. I mean, R is not a discrete field.
And the problem is managing to getting out of the modality. So you apply this modality that allows you to pretend it's a discrete field, but in the end you want result without the Nabla modality, and how to get out is it's a difficult question.
Usually you can get in. Usually you cannot get out. It's like a layer.
That's the dynamic.
You guys can make like a general uninformed comment.
Oh yes, please.
Like usually you think about what kind of hypotheses you want to make and prove something. The one person will just try to prove it. See what you actually need in order to prove. So you take some results about curves that you expect to be true, and then you try to do it synthetically. And then in the process of the proof, you should be able to figure out what where the actual assumptions has the direction.
Yeah, that's what I
Usually
said.
it's hard to like get before and.
Yeah, that's what I said. You should try to prove things and wait until you get stuck and then assume what you get. And if like the thing causing you to get stuck looks reasonable, you assume it should be true. But it's probably, I don't know, it looks like a good idea, but. Yeah, but I guess we don't know what is we don't know very well what is actually reasonable and what's not.
Yeah, you want some kind of balance because we will still want the examples for each of I and also.
And I guess if you're just considering more specific curves, then I guess there's a way to do. If you only consider specific curves, there's usually a way to like define those functions. Even if you're even if you say we will consider only planar curves, that is curves that can be curves that can actually be defined as the zero set of a polynomial. Maybe maybe if your curve is explicit, there should be a straightforward way to define these things, but for more general abstract curves, yeah, you don't have that.
Yeah, maybe not all divisor has a degree, just
Yes.
some that just
Yes.
the well-behaved one, and if the one if we want to use Riemann-Roch with the well-behaved one.
And we know that constructively, and that actually makes sense. We know that constructively not all vector spaces have a dimension. So, why would you? Why would you expect that every divisor has a degree? But yeah, another thing is that we can actually start with say a class of curves like say elliptic curves and compute all these things explicitly, and yeah, I don't know, if you're only considering division on elliptics, I would expect say all divisors to have degrees, because why not? There's no reason to think otherwise. And the construction should be pretty explicit. So.
Yeah. Okay, so thank you again. And actually, this is the end of the day.
Okay.
Yeah. So yeah, at least I will stay here with some algebraic geometry. It's a good if you want.